Circular motion. So before we can talk about circular motion, we need to go back and look at what net forces do. So we already said that a net force produces acceleration. Now, what does that mean? Well, remember that acceleration is a change in velocity, and velocity is a vector. So how could we change our velocity? We could speed up. What else could we do? Well, changing velocity isn't just going up, it could also be going down. So that could be slowing down. But remember that because velocity is a vector, if you change the direction you're moving in, you're also accelerating. So that could be change direction. So once again, a net force produces acceleration that makes you speed up, slow down, or change direction. Well, this change in direction, that's going to be our circular motion, or it could be going around a curve, okay? So let's look for a second more specifically at speeding up. Speeding up occurs when the net force and the acceleration have the same direction as the velocity. So let's say we have a block here, and the total force on the system is to the right. Well, if the net force is to the right, the acceleration is to the right. If it's moving to the right and has a net force to the right, then we know that these two are in the same direction, and that's going to speed up. Slowing down occurs when they're in the opposite direction. So if the F net and A are opposite the velocity, you're going to slow down. So let's say V, the block is moving this way, but it has a net force this way. It will accelerate this direction, and when these two are opposite, it's going to slow down. So we already know that, but what happens to create circular motion? So for circular motion, we said that there's going to be a net force that's going to act to change the direction of the velocity. So when does that occur? So let's say this is a top-down view of a car driving around in a circle. So what direction is the car moving? If you think about the headlights of the car shine in the direction of the motion of the car. So the headlights shine straight ahead, so that's the direction of the velocity of the car. But the direction of the force is perpendicular to the velocity. So the net force is this way. Now, if the net force is to the right, then the acceleration has to be to the right. So when we have a net force producing an acceleration towards the center of a circle, the velocity is perpendicular to that net force and that acceleration. That is going to produce a change in direction, and that change in direction is going to give us this curve, specifically a circle. When the net force is perpendicular to the velocity, it has a name. If it's perpendicular to the velocity, it's acting towards the center of the circle. So we call this net force a centripetal force, but don't forget that it's still a net force. So that centripetal force, how can we remember that it acts to the center? The word center is almost written in centripetal force, is the center-seeking force. And the abbreviation is FC, and that C helps to remind us that it's towards the center. But again, I have to stress this, especially if you're doing more advanced physics, that centripetal force is a net force. And what does it produce? It produces acceleration, but not any old acceleration. We call this a centripetal acceleration. So what is centripetal acceleration? Well, regular acceleration we said was change in velocity over time, but there's an additional formula that's specific, and this specific formula is AC equals v squared over r. And the units, if you derive them, still comes out to meters per second squared. That's meters per second squared, all of that divided by meters gives you meters per second squared. So, what's the most important thing in this unit that you're going to get tested on? Well, the most common questions deal with what direction these three quantities are in. And centripetal force always acts to the center. And when we say acts to the center, it's acting to the center of the circle, or if it's part of a circle, then we would say the curve. Centripetal acceleration also always acts to the center. Now, why is that? It's because net forces produce acceleration in the same direction as the net force. So that's a net force, so it's going to produce acceleration in the same direction. And the velocity always acts tangent to the circle. So let's look at a circle here, and we'll do this as an example problem. And let's say that the ball is traveling around in a circle clockwise. So it's cruising around in this direction. And we're defining our directions of north, south, east, west off to the side here. And let's look at the directions that FC, AC, and V are going to act in. So the velocity is going to be tangent to the circle. So what is a tangent line? A tangent line, you know from math, is the line that is basically straight off the edge of that circle right there. So at this point, the velocity acting tangent to the circle is going to be that direction. And we know that the centripetal force must be acting perpendicular to that velocity. What's perpendicular to that velocity? That's the force that's acting to the center of the circle. And because this is a net force, it produces acceleration in the same direction. Now, it really doesn't matter whether you make this vector shorter or longer. I'm just making it shorter so that we can see it more easily. But the key idea is that they're acting in the same direction. So what direction is velocity acting? It's acting to the east. What direction is centripetal force and centripetal acceleration acting? To the south. Now, this does seem sort of tricky or non-intuitive, that something's moving this way, but being pushed to the center of the circle, yet it's not getting closer to the center of the circle. But think of it this way. If there was no centripetal force, what would the ball do? The ball would move in a straight line. That is Newton's first law. So if there was no centripetal force, the ball would move out to a position here. Well, what did that centripetal force do? It moved the ball towards the center of the circle to here. So in actuality, the ball was moved to the center of the circle. It's just moving it from where it would have gone if there was no centripetal force. We know that F net equals ma. But what happens if we say that this is centripetal acceleration? Well, what causes centripetal acceleration? Centripetal force. So our formula is Fc equals mac. So they give us this formula, Fc equals mac, but we also know that AC is v squared over r. So we can substitute in v squared over r into AC. So if we do that, we have AC equals v squared over r, and we take this and substitute that in, then we can say Fc equals mv squared over r. So this formula is not given on the reference table, but it is a way to solve for the centripetal force. So let's go ahead and solve a problem. Let's say we have a car that's traveling around in a circle counterclockwise. So that's going to be this direction right here. and we're given the car mass, the speed, and the radius. Now remember that when we're talking about the velocity, we have to include the direction, but the speed is referring to how fast the car is moving at any point in the circle. So the speed means we don't have to take into account the direction. The radius of the circle is obviously from the car to the center. So the first question is, find the centripetal acceleration and the centripetal force. So we know that centripetal acceleration is v squared over r. So we can just put in the numbers. We have 20 meters per second over 180 meters. So that's going to give us a centripetal acceleration of 2.2 meters per second squared. To find the centripetal force, we could do Fc equals mv squared over r, but we don't need it because we already have AC. So we can just put in 1,200 kilograms times 2.2 meters per second squared, and that gives us a centripetal force of 2,640 newtons. Remember, these are vectors, so we need to include direction. It says label velocity Fc, v, Fc, and AC. So what's the direction of these velocity, centripetal force, and centripetal acceleration? Well, if it's moving in this direction around the circle, what is tangent to the circle? Well, our tangent line looks like that. So our velocity is going to be south. What direction is the centripetal force? Remember, centripetal force always acts to the center of the circle. So that's going to be our Fc. And our centripetal acceleration always acts to the center of the circle. So that's going to be the direction of AC. So Fc and AC are to the east. The last question says, if there was ice, so let's say this car is going around this circle and friction is what is driving the car around the circle, and the car hits a patch of ice, there's going to be no friction to push it to the center. So therefore, what direction is it going to move? Straight. And the car is going to go off of the curve and land at point B. So this is getting into slightly more difficult physics for centripetal force, but we need to understand this to be able to solve problems like derivations and questions where we actually have to take the centripetal force and substitute in a new force. So let's say we have a car driving around this curve like this. We would say that the centripetal force is acting to the center of this curve. But what is the centripetal force? Remember, it's a net force, so something needs to be causing it. Well, what's pushing the car around the corner? If there was no friction, the car would travel off in a straight line. So the net force, the centripetal force, Fc, in this case, is Ff. So if we were to write a net force equation, we would write F net equals ma equals Ff. But because it's a centripetal force, we can say Fc equals mac equals Ff. What would it be if it was the Earth going around the Sun? Again, we have a centripetal force that acts to the center of the circle. But what is that force? It's the force of gravity. So we would write our net force equation, F net equals ma equals Fg. But in this case, F net is a centripetal force, so we can say mac. And what is the force of gravitation between these? Well, we could put in g m1 m2 over r squared. And finally, if we have a roller coaster, and let's say this roller coaster is going around in a loop, the centripetal force is acted towards the center of the circle. Now, if the car, the little roller coaster cart, is going fast enough that gravity is not enough to push down on it, the track is also going to push down. So we have two forces that are acting as the centripetal force, and that would be the the force normal of the track, and the force of gravity. So our net force equation would be F net equals ma equals Fn down plus Fg down. What could we do to solve it for centripetal? Well, we would just change that net force to Fc and mac. Okay, what we have here is a car that's going around a banked curve. If you've ever watched NASCAR, in the races, they bank the corner up, which helps the cars to go around the corner. It gives them an additional force that's directed towards the center of a circle. And we're going to see what that force is in just a second. So when we see this car going around the corner like this, we're going to draw our diagram in 2 dimensions, looking at it from only this perspective. So when we see this, what we're looking at is the back end of the car as it drives around the corner. So the question is to find the minimum speed necessary to round this corner without either slipping up the plane or down the plane. Now remember, it doesn't actually move up relative to this point. It moves in a straight line, but that direction from the perspective of the car seems as though it's going up the plane. It's only going forward. So remember that we always break up forces in the direction of the plane of acceleration. Now, this is our curve, so if we followed this curve around, the center of the circle is over here. So our plane of acceleration is towards the center of the circle. That's going to be where our centripetal force is pointing. So we only have 2 forces in this case. We're ignoring friction, so we only have the force normal and the force of gravity. Well, none of the force of gravity is in the plane of acceleration, so we don't have to worry about breaking that up, and that's not going to be in our net force equation in the x-plane. However, sum of force normal is up, and sum of our force normal is to the right. So this force right here, the component of the force normal that's acting to the right, we're going to call that Fnx, and we're going to call this upward component Fny. So we can see that this force is going to be our centripetal force, and this force is going to be equal to the force of gravity in the opposite direction, and these 2 are going to cancel, which is why it doesn't accelerate up into the air or crash through the ground. Now, there's another couple of tricky things here, which is that this angle theta, as we've seen before, is equal to this angle theta, and from math, geometry, we know that these 2 must also be the same. So let's go ahead and break this up and solve it. We're doing this problem as a derivation, so we're not going to be putting numbers in. So here's our free body diagram, and we're breaking this up into the plane of acceleration. So we have our Fn y and our Fnx. And we know that this is our theta, so this is our theta here. So when we look at this side, this Fny, what is that in terms of theta? Well, we have a right triangle, and we know that this side is Fn. So if we're looking for Fny, we can do cosine theta. So we can say cos theta is equal to adjacent over hypotenuse. In other words, cross-multiplying, Fny is equal to Fn cos theta. And likewise, if we're looking for the x component, our Fnx, that's going to be equal to this side of the triangle, which is our opposite. So we can say sine theta equals opposite Fnx over the hypotenuse, which is Fn. Or we can say Fnx is equal to Fn sine theta. Okay, so now let's write our F net equation. So we'll start with an F net y, and we have to define our directions. I'm going to call up to be positive and to the right to be positive. So we have our F net y equals ma, and what's acting in the y direction? Well, we have Fny is up, and Fny is going to be our Fn cos theta minus our force of gravity down. Now, in the y direction, there's no acceleration. It's not accelerating this way or this way, so that drops out to be 0. And we're solving for Fn, so we can bring this mg to the other side because that's 0. Whoops, 0. So bringing that over, that becomes Fg equals Fn cos theta. And if we bring this cosine theta over here and replace this with mg, we have mg over cos theta equals Fn. And I'm just going to flip this to the other side and write it as Fn is equal to mg over cos theta. So now we can do our F net x. So F net x is going to be equal to ma. But this net force is acting in the plane of acceleration, which is towards the center of the circle. So that's an MAC. So that's going to be equal to the only force that's acting in the x-plane. The only force that's acting in the x-plane is Fnx. And we know that Fnx is Fn sine theta. We know that AC is v squared over r, and we know that Fn is mg over cos theta. So we can say mg over cos theta times sine theta. We have an m on both sides, so we can divide through by m. And we know from math that sine over cosine theta is tan theta. So that becomes g tan theta. And on this side we have v squared over r. Multiplying through by r, that gives us v squared is equal to gr times tan theta. And then taking the square root of both sides, we end up with the square root of gr tan theta. This is called the Gravitron Problem, and this is a ride in amusement parks where they have a large cylinder that spins around in a circle. And the person stands against the wall and the floor drops out and the person sticks to the wall. So the question is, how fast do you have to spin this gravitron so that the person doesn't slide down the wall? We're going to say that the radius of this is r, and we're going to do this as a derivation, so no numbers. So what forces do we have acting on the person? Well, we have Fg. Now, what counteracts Fg? What keeps the person from sliding down? Well, that happens to be friction between the person and the wall. Now, why is there friction? Well, because there's a normal force. The wall pushes against the person to the center of the circle. The wall pushing against the person, that's Fn, and that is going to be our force that's acting in the plane of acceleration, so that is our net force, that's our centripetal force. So let's start out by writing a net force equation in the y direction. We're going to do like we did before. We're going to call up and to the right as positive. So we have F net equals ma equals ff up minus fg down, and there's no acceleration in the y plane, so a becomes 0. I'm going to add this fg to the other side, so that becomes fg equals ff. And we can say Fg is mg and force of friction is mu Fn. Now the person is not sliding, so that means that this is mu s, or static friction. So what is Fn? Let's divide through by mu s. So we have mg over mu s is equal to Fn. And I can just flip this equation around and say that Fn is equal to mg over mu s. But there's no velocity in this equation, so we need to solve for v. And the way that we're going to do that is with an F net x equation. So we have F net x equals ma equals, and what's the only force that's acting in the plane of acceleration? Well, that's our Fn. So we can say F net x equals ma equals Fn. A, we know this is a net force to make something go in a circle, so that's AC, which we can replace with v squared over r. And that's going to be equal to mg over mu s. So masses cancel out. We have one on both sides of the equation. We multiply through by r, so that gives us v squared equals gr over mu s. And we take the square root of both sides of the equation, and that gives us the square root of gr over mu s. Notice that mass is not in the equation. In other words, this is a mass-independent ride. Mass does not matter. All right, we have a ball swung in a vertical circle. So this would be as if somebody is standing on the ground and they have a rope and they're spinning this ball around like this. Okay, so gravity is acting down. This is in a vertical plane. So this ball is going to spin at a constant speed, but we want it to go as slow as possible and still make it around the top. In other words, it's just going to make it over the top. Now, if that's the case, then we don't need to pull down on it. We only need gravity to act as a centripetal force to make it go in the circle. So our free body diagram at the top would be only Fg. Fg would be the only force making it go in the circle. So at the top, we have our net force equation. I'm going to call down to be positive. F net equals ma, and this is our plane of acceleration. This is the way that it's accelerating. So that's going to be AC equals, and then that's going to be the force of gravity. So if we replace AC with v squared over r, then we have this Fg is mg. We have m's on both sides, and we multiply through by r, so that gives us gr, and then we take the square root of both sides, which gives us v is equal to gr. That's the minimum speed needed for the ball to round the circle. But this speed remains the same, and when it gets to the bottom of the circle, now we need some force of tension to lift it up, because the force of gravity is working against us. In this case, the force of gravity is acting down, is helping us to make it go around the circle. Here, force of gravity is acting away from the center of the circle, so we need additional force up to help us provide enough force to make it go in a circle. So to do that, at the bottom of the circle, we're going to have the force of gravity down, but then we need an additional force of tension up to help make it go in the circle. So our net force is going to be Ft minus Fg in this case. Now, to keep everything positive, I'm going to call up to be positive in this equation. So we have our net force equation, F net equals mac. Our plane of acceleration is in the vertical direction, so that's going to be centripetal. And then we're going to have Ft minus Fg. So AC becomes v squared over r, and mg Fg becomes mg. So, to solve for v, we know that v is the constant speed that we solved for in the problem before, gr. So we can sub in m, and then that's going to be the square root of gr squared over r is equal to ft minus mg. Well, a square root squared is just going to be itself, so that's going to be mgr over r. And we have an r on the top and the bottom, so those will cancel, equals ft minus mg. So we have mg on this side. We're going to add another mg to the other side, so that's going to make that become 2mg equals ft, or rearranging it, the force of tension is going to be 2 times the weight.